everyone. I'm Jeremy. I'm a developer for Code Construct. I'm also going for the prize for the furthest distance travelled here today. We're based in Australia, and we do essentially software consulting around like a heavy open source focus, embedded systems, and we've been doing some neat things around storage management, storage control. And all of that, like a lot of the stuff we do, is all open source, and it's all mostly upstream now and kind of available to use. So today, kind of going a bit of an overview about what the stack does, what all the components of it do, how that all fits together. Because fitting together is a pretty important thing here at the moment. Interoperability is a big part of that, and so this talk is a tale of many standards. We have a lot of different components. We have a lot of interactions between those components, so it's important that we can get all these things talking together with minimal sort of fuss. So fortunately, it's a nice stack of standards rather than a giant pile of standards, which really helps us here. A couple of caveats though. I'm talking about quite a few different parts of the stack, of the management stack of storage devices here. So there's probably going to be bits that you already know about very well, but there's also going to be bits that aren't so familiar. And also this is covering a lot of open source components. So we did a lot of integration work and we built some of these components all from scratch, but as with anything in the open source field, we're sort of standing on the shoulders of other giants in doing a lot of the heavy lifting in terms of providing an operating system, providing a lot of infrastructure, and providing a lot of the standards work as well. So I guess we're going to start our walk through the stack at the bottom of the layer here. Oh, sorry. What do we mean by the open out-of-band management side of things here? Typically, in a storage system, we'll have our host performing I/O interactions with some sort of storage. In our examples here are an NVMe subsystem. When we're talking about out-of-band, we're not necessarily going to be communicating over this I/O interface here, but instead we have a sideband of control, of monitoring, of kind of other things that aren't our main sort of host interactions here. So when we're talking about out-of-band, we're kind of talking about what's happening on the left-hand side, where we've got our storage subsystem talking to some sort of other management controller that's not our main kind of storage hosting device here. So in those cases, we generally do things like inventory management, finding out what devices are present, and also super important, what devices might be absent. We want to look at doing device monitoring, things like monitoring your thermal envelopes, seeing how the device is going, making sure it's healthy, making sure it's serviceable. A bit of device control as well. That can mean a few things. We'll go into sort of what some of our options are here. And one that's becoming super important at the moment is firmware management, making sure we have a stable configuration of our stack, making sure we know what's running, and making sure we can upgrade it when we need to. We can also do a bit of actual I/O over these sideband interfaces. I would kind of discourage that. There's some facilities to perform some pretty weird things over these sideband interfaces, and I'm going to cover why that's not basically why that's not such a great idea. So getting into it, we're going to start from the bottom layer of our stack here. In the PCIe spec, we have a couple of signals here, the SM clock and the SM data lines. So this is super, I guess, early in the PCIe spec. We have our SM bus connections here. On our M2 connector also, we have the same set of things on pins 42 and 40. On the U2 connector, we've got the same thing here. So we've got this common theme about having this SM bus out-of-band interface present in the standards, ready to use for our sideband channel of management of these devices. The device support, or the baseboard support for those can be, I guess, unpredictable. So we built a little carrier for M2 and U2 devices. So this gives us our gives us enough power and enough bootstrap of getting a device booted, and then we can talk to the SN bus interface through this, through to any other kind of I2C SN bus host. So that allows us to do a bit of debugging. It's certainly not a production part. It just helps us with our own bring up in getting the management side of things, talking to our development environment. So walking a level up the stack here, over those signals we have our SN bus I2C channel. I won't go too much into detail about I2C. I think probably everyone's somewhat familiar with it. Super old standard. The important thing here is that it's a shared bus. It's addressable. We typically have a whole bunch of devices on one I2C channel. And in our cases here, we're running it in a multi-controller configuration. So there'll be, it's possible for multiple devices to be mastering that bus at any one time. Well, not exactly at the same time, but coordinating and arbitrating for access on that bus. There are a few limitations of this. We've got, I guess here are our standards. We've got an element of kind of a maximum size really defined by these standards about what sort of transactions we can do on the bus. And the messaging format is super simple. So in fact, this is all we have really. We have a message with an address and everything else is arbitrary. So this is a enumeration of an NVMe device on our bus, an example in our case, and it's presenting 3 different endpoints. These addresses are somewhat standard. It doesn't really matter what they're doing now, but we have a way to enumerate what's on the bus and talk to these devices on a simple sort of messaging format. So at that level of communication, we can do a few kind of management-y type things. We can interact with typically this 53 address here to download some EEPROM data from our M2 device or our whatever PCI device to tell us what it is and give us some basic capabilities about it. With some NVMe devices, we can do a little bit of management. There's a little corner of the NVMe-MI spec that allows us to do some things here, but we can certainly improve on that by kind of building up our stack a bit. The first thing we can do is add a bit more of a transport layer on top of I2C. So the management controller management component transport protocol, MCTP, is a standard that gives us a bit more of a messaging protocol between management components. So particularly in our case, we're looking at having a management controller talking to an NVMe device, but it's not limited to that. We could have management controllers talking to network devices, to the host. It's basically a fairly simple transport protocol intended for these kind of management operations which we're looking at with NVMe here. The MCTP spec itself is transport neutral and comes with some binding specifications. So this one is our SN bus binding spec for MCTP, and it tells us how an MCTP message is transported over the SN bus. This is what a MCTP payload looks like over I2C. So we have a very small header on that. And then inside that, we sit a common MCTP payload. So working up the stack here, we have a message format at the bottom that sits on a transport-specific message format, which sits on top of I2C. So this is our method of getting essentially a transport-independent way of sending messages around a management bus, in our case between NVMe and a management processor. So there is an open implementation of MCTP all upstream at the moment. We wrote a kernel level network protocol support into Linux. So we can treat that just as basically as a socket interface. So you can open a socket and then communicate with MCTP devices based on their MCTP standard addresses. So we upstream that, and we've written some basic tools for MCTP in terms of setting up your stack in Linux. So configuring addresses, setting up routing tables, all that sort of thing is now all upstream and working, and allows us to get a base layer of messaging around a management system. So walking up the stack again, so the folks at the NVMe group defined a management interface, and it's basically it's kind of a little subset of device management it's nowhere near the full sort of comprehensive set of things we can do over NVMe, but focused on sort of management of the device in terms of looking at the bit of inventory information, things like thermal monitoring. We have temperatures available over this NVMe-MI interface, and it's defined to run over MCTP. So there's a subset of the MCTP spec that tells us how to serialize NVMe-MI messages over our MCTP protocol here. So again, very lightweight, very small messages, and gives us a first step into managing NVMe devices through some fairly simple messaging commands. In our case, we have these small payloads that are sitting on within our MCTP stack here. Interestingly, we have a little type field in MI, which I'll go through in a bit. But at this point, we can get some comprehensive inventory data and our subsystem and controller health out of the device. In terms of the implementation, we have some support now in the open source libnvme project, which performs the MI messaging commands over the support we added into Linux in our socket interfaces. So that's maintained by the existing Linux NVMe project, and the contributions there add the MI support for that in a somewhat intentional way of kind of matching how the existing API works for NVMe in general. So this gives us some methods of writing standard Linux programs against an existing kind of library interface that can do our MI messaging. Within MI, we have, I mentioned that type field earlier, this one here. Within MI, we have options of different command sets that we can run over these MI messages. The first and the kind of default being our set of MI commands. We also have the option of sending actual NVMe admin commands over this MI interface. So this gives us the full subset of, well, I guess whatever the controller supports, but the potential for the full subset of admin interface that we can perform over this sideband channel like we're directly connected to an NVMe-MI device. So that can be quite powerful in terms of managing the device. And we have access to essentially the entire admin component of the NVMe base spec, which is kind of cool. So we can do things like do a normal admin identify command. Again, this is running entirely over our SM bus interface and not involving the host at all. So in this case, the PCI connection to the NVMe device can be completely off, the host itself can be off, and we can issue admin interface commands to the device. In this case, identifying it. We can also access the firmware log page, which tells us which versions are running on that device. And even cooler, we can download new firmware to the device, again, with the host completely off at this stage. So this gives us some fairly kind of comprehensive management systems in kind of this out-of-band channel. And that's handy for cases like we may have a cloud environment where there is separate ownership between what's running on the host, and that might be owned by the customer at one point, and then what's running on the management sort of infrastructure of our cloud provider, which is run by the cloud provider themselves in terms of their infrastructure management processes. So this gives us our full NVMe admin functions over this sideband interface. Again, we're making use of some existing open implementations. We've got the libNVMe library here. As opposed to our last set, this is not the MI additions we added. This is just the core standard libNVMe parts, which we've hooked the MI interface to as a backend in how you communicate with the device. So there are we still need to do per function kind of abstraction of the channel we're using to talk to the device, but the API on the client side remains exactly the same. We can just call identify, we can call firmware download, and it all looks the same from the client side up on that. In the same way, the existing NVMe command line utility, because it's backed onto libNVMe, just uses those same functions, and now they're available over our sideband interface for sideband management of our NVMe devices. One thing that's happening as we're working on right now is Klaus, who's I think 2 rooms over and speaking at the moment, wrote a MI model in QEMU that allows us to essentially emulate the sideband of an MI device, and we can now run our management controller entirely in QEMU with an emulated connection to an SM bus NVMe device. And that gives us some really interesting options in firstly developing our management stack without having to actually deal with physical hardware, without having to align our firmware that's running on the NVMe device itself with the changes we want to make. We can kind of develop those and model them in kind of synchronous processes in terms of writing new emulated MI firmware and talking to our management stack for that firmware at the same time. So that's pretty cool. Klaus has been working hard on that, and it's not his day job, but he is doing some great things there. And we've been adopting that and getting our management stack talking to QEMU in that regard. So that's great. We can do all of our commands. We can do our standard kind of things from a Linux interface to a management controller, which is running. In our case, we're using OpenBMC for all of this kind of stuff, and we have a local interface to our NVMe devices that we can access through the shell on our management controller here. That's all well and good, but the real value in this is not having to log into a machine to locally manage a device. We want some remote way of talking management sort of commands to some remote node, and that's typically in a data center environment. That's typically your provisioning infrastructure. We kind of, I guess you can probably see where I'm going here. We need some way of doing some standard protocols to operate our newly found NVMe management commands. And of course, that's Swordfish. So this is where the standardization becomes super important, in that now we're talking off node. We need a standard, reliable way that retains compatibility between the functions that our management controller and the functions that custom written management infrastructure need to talk to. Now, in continuation with our standards, this is the Swordfish spec, which gives us a, I'm not going to into this too much because I think everyone here is pretty familiar with this so far, but it gives us a description of an API, works over REST, extending on the Redfish interface, allowing remote access to the NVMe objects that we can now talk to over NVMe-MI, over MCTP, over I2C to the physical devices. So as a 4-slide overview for those who might not be familiar, this gives us under our service route, we have a description of, we have a set of systems. Under those systems, we have a set of storage devices. In our case, we have, in this example here, we have one NVMe storage device, which represents our subsystem, our NVMe subsystem to manage. One fairly important thing, I just learned this was fairly recent, but having a NVMe, Swordfish provides an NVMe mapping guide, which is super important in kind of matching up what we've got on the API side with the actual concepts in the NVMe spec about, in this case, the storage object represents our NVMe subsystem. So here we've got our subsystem, and the actions that you can perform on a storage subsystem are all kind of accessed this place in the URL namespace. Under that, we also have a set of controllers, and they map to our NVMe controller objects, which we can do things like our identify command that we could do with the command line before. This kind of maps that to a remote access facility for an NVMe controller. As well as that, we have volumes present in our Swordfish namespace, and those map to our NVMe namespaces. So we can perform namespace management operations at this object in the REST hierarchy of Swordfish. So we've been working on some little bits recently. I think in coming into this project, a lot of the functionality was already defined, to the credit of the Swordfish folks. We've been adding a little bits here and there that our clients have been needing. The first one is implementing the SPC5 security protocol interfaces. So this is present in all the way back to the SCSI standards about sending somewhat opaque security-related commands to and from the drive. So those are now present in the Swordfish spec. We've been doing some tweaking around how we manage namespaces through the Swordfish interface, making sure we can describe things like the LBA formats and having a facility to create and manage namespaces under the NVMe, the REST hierarchy there. So those are the bits we've sort of been working on that level, which gives us essentially a full set of NVMe admin functions, and not just on the local management controller, but exposed outside the system to external management infrastructure, allowing kind of scalable and remote and open interfaces to our NVMe storage. And all this can be done while essentially completely out of band and completely independently from what might be happening on the kind of I/O interface between the host and the storage as well. So it gives us this, I guess, a separate management channel into our devices. Again, using the Swordfish spec here. So the implementation side of this, we've been working heavily kind of on an OpenBMC basis here. The dbus sensors project provides the infrastructure for that, and we've been working on that in conjunction with a few others in the community on adding the NVMe admin interfaces through to the infrastructure provided by dbus sensors. Once that's done, it gets exposed through standard OpenBMC facilities into the REST API and the Swordfish API through that. There's a few kind of considerations around how we do all this. And And I think this kind of becomes a bit of a design discussion, but some of the things we've kind of learnt through the process is, firstly, the I2C layout can really affect what's possible on a system through essentially contention on the bus. A lot of folks, I guess, coming from the sort of PCI side of things have tended to put I2C multiplexers around, which has some interesting interactions with how MCTP itself can work. So we've sort of learned some lessons around there and have some thoughts on how to architect a system that is manageable through these interfaces. Another thing that we found is super important is essentially spec compliance, and there's been, I think we've gone through about 8 specs here so far, and there's often little kind of bits. We're coming in from a space that I guess embedded systems can often be a bit developed all in unison, so there's less of a focus on having a decent spec to rely on in that regard. So now that we're using things like the MCTP protocol, we're using things like NVMe-MI, which give us, I guess, a bit of a promise of interoperability. Making sure that we actually are interoperable allows us to take advantage of things like having our management stack open source, pluggable from device to device. So we found some little variations on vendor hardware in terms of even things like timing of the I2C stack has been interesting, and we have had to add a few quirks into some of the layers of the stack there to work around little spec compliance issues from devices. That's not necessarily a huge drama, but we don't want to get into a case where that's no longer scalable. We want to make sure that we can have a bit of kind of plug and play type attitude into the field where that may have not always been the focus before the point where we're using sort of heavy standards on this. One thing we're looking at the moment as well is how we can verify that devices sharing communication under MCTP can, how we can make sure that's guaranteed to work under different conditions as well. So I mentioned earlier that the I2C bus needs to support multi-master situations. We kind of get towards the edges of I guess, compliance in that regard as well, in things like bus arbitration, things like fairness algorithms that these devices participate on the bus. So there's a few considerations there and a few lessons we've learned along the way about how we can scale this out to kind of hitting the maximums of how many devices we can have how many devices we can have on an I2C bus, and how these devices can play fairly with each other in terms of their messaging, while under some potential fairly demanding management operations like a firmware update, which we can be sending 3 or so megabytes of device firmware over a bus. We need to make sure that's scalable when we're kind of expanding these management capabilities. Also, the security implications of all this is fairly important. It's possible that we're allowing things like an arrays operation over a sideband channel, which the host might not be expecting at any time. So we're going to make sure that when we're architecting the sideband channel in parallel with a host channel that might be on a different trust domain, that we're kind of considering what the expectations on both sides of those domains are. So that's kind of a newish field as we get more and more functionality available over not just the I2C SM bus interface, but also remotely accessible over Swordfish. So that's becoming more and more important at the moment as well. A few kind of resources here. Rochelle on the SSM has been super helpful in getting this going, having a lot of guidance on how this should work and how the standards kind of provide the way we should be implementing this, the way we'd be structuring the code, and the way we're providing our implementation and recommendations to those kind of looking at their vendor implementations and the management implementations as well. We've got a few documents up. There's a few kind of bits of guidance on MCTP support, on the NVMe support as well. And of course the general Linux NVMe project, that's where we're upstreaming all of our NVMe bits to, as well as the MCTP support itself in the kernel. That's mostly it. Is there any questions around the NVMe bits there? The management bits? No? Oh, sorry, yes.
I would be curious, but I'm not sure. This may be a very broad topic. Do you have a little bit more information? Would you elaborate more about the I2C layout, related MCTP considerations that you mentioned in terms of, for example, how many devices per bus you experiment with, or I don't know, the max, you mentioned max devices on the bus, how they influence the interactions with the device. Can you elaborate more?
Sure thing, yeah. So the question was, the question was, what our experience, can we have any more detail about our experiences with the I2C considerations and things like the muxes and maximum devices? Was that all of it? Cool. So that's something we've started some work on just in the last month or so in characterizing what the I2C implementations look like at the moment, and that's we're starting there by looking at what the I2C controllers, how they behave in the face of not getting a bus idle period in when they expect to, how they handle contention on the bus, and arbitration loss. So we are getting close to what I think the original device manufacturers expected as limits in what the arbitration loss, how long they lose arbitration for, how many times they have to retry. So there's, I guess I don't have any particular recommendations, but more about testing on that area is kind of super important. And we're kind of, I guess, launching a bit of our own, just a bit of a skunkworks project on trying to characterize what these controllers will do in those situations. So that's on the implementation side. On the layout and system design side, I think if we can avoid muxes, that's probably the way to go. We're seeing management controller designs coming out with a whole lot of I2C buses that are direct, which is great. We'd have to deal with muxes, it's all sorted. If we do introduce an I2C multiplexer into the architecture, we have to be really careful about making sure that we have I guess, synchronization about when we expect to reply to an MCTP message and when the mux is changing state. So we did, in the kernel MCTP driver, we have support for muxes, but essentially it relies on the mux has to be locked into a particular configuration while we're waiting for a reply on any message, which kind of it basically introduces a whole lot of locking between different transactions, which isn't great. Whereas MCTP allows us to have multiple in flight at any one time. We have to reduce that down into one per mux subordinate at any one time, which isn't great, but we have to know it's just how it works, right? We just can't receive a reply if we switch the mux around. So, but yeah, good question on that. And the third part there, maximum number of devices. I guess there's two parts. There's electrical constraints, which are kind of, I guess there's components of the SM bus spec about things like maximum capacitance. I think I'm not an AE, so I kind of can't comment too much about that. But we firstly want to make sure that we have the physical capability of communication, but also getting back to my first point about how we manage contention on the controllers, and essentially everything is a controller because it's all multi-master, but how the firmware implementation of these devices stands up to contention on the bus, essentially. So that becomes more of a testing effort on kind of everyone's side about making sure that we can put 20 devices on a bus and they all behave in the way we expect. MCTP does define a fairness algorithm. I don't think anyone implements it, but that's again more of a sort of a testing effort to make sure that when we hit these cases that we're not kind of digging ourselves into too much of a hole. But yeah, I mean, essentially, this is kind of a firmware problem. So it's fixable. Like we can always do more QA. We can always do more testing. We can always do more kind of consideration about these corner cases to improve the situation in our kind of system design from here. So yeah, great question. Thank you. Yes.
So this might be a silly question, but for the MCTP info on Linux and the capability of sending admin commands,
yes.
do you need to be root or have capsys admin to set up that communication channel and send the commands?
So going back to what we hear, question is what permissions or what credentials are required to be sending admin commands? So essentially, to open an MCTP socket is the same as opening any other socket. You do not need capsys admin to be performing outbound communication. So hence the security implications of what we're doing here in allowing untrusted users, I guess. It's a bit tricky because we don't have the same, we don't quite have the same kind of user model on the management controller as we would on the host system, but there is no specific constraints on opening an NVMe-MI socket on a Linux system. It's certainly as with any kind of networking infrastructure that you need the capsys admin to be able to administer the layout and set up your routing tables, assign addresses. But once that's done, you essentially have access to the MCTP bus as any kind of network app would. We do require capsys admin to bind, which is kind of expected as well, and that's when you'll be implementing your NVMe-MI responder, but that's not what's happening in this case. So again, having some sort of security model on opening sockets to devices is fairly important in this area. So given the amount of control you can have over an admin interface. Does that answer your question? Is that,
it does.
cool, thank you.
Yeah. So
Sure.
just as a note, and maybe so the NVMe Linux service. Thank you. We've developed. Okay. The NVMe Linux service that we've developed that sits on top of the NVMe CLI. We've addressed a little bit of the security by we're going to require it to be run as root. And this is one of the reasons for that.
Yep.
So when you create a Swordfish service, then you have to have roles and you have to have accounts and such service. But requiring it to run as root further limits the restrictions when it's running as a service. But if you were in the last, I don't think you were in the last service or last session, but John and I were describing the one that Intel was built, and we sit on top of the NVMe CLI for this implementation. But it runs on Red Hat. You can download it, but it will have a restriction that must run as root, specifically to close source.
Yep. So in Rochelle's case, you're dealing, correct if I'm making assumptions here, but you're dealing with in-band communication with the host. So that's using your standard NVMe device nodes because we're going through NVMe CLI, right? In our case, we're not, and we're just opening a socket and going through there. So we've, I guess, different sort of user space permission constraints on in-band versus out-of-band. And that becomes a kind of a threat model on the BMC itself, which, you know, there's a lot of security considerations to go around here. So whether it's...
Right, yeah. So I was actually correct. Sorry, I was jumping ahead. We're talking about also creating one that would talk through with the BMC, and that's the other case.
Right, sure, yep, absolutely. Sounds good. Anyone else? Any other questions? Yes?
Maybe one more regarding the interaction between the BMC and the devices. Did you look into, like, I would say, new extensions that are planned for these types of communications? So, for example, security extensions related to encryption of the channel, or maybe NVMe-MI is going to have some asynchronous others or things like that. So, did you look at how such use models could be implemented? Experiment with this.
So the question was, in implementing this, did we look at any of the extensions, including security and the asynchronous models through? Yeah. The security side of things, not in the channel itself. I think we'd be relying on folks doing, say, an SPDM setup for our channels here. I think there's a whole, I guess, different kettle of fish in what we were doing for the security protocol in, security protocol out commands in establishing a trust relationship with the device. And that's all TCG communication, that provides its own trust architecture between management node and the device. And in our case, because we've exposed that through Swordfish now, that extends that endpoint. The endpoint no longer has to be local, so we can use a remote provisioning service to establish a trusted peripheral relationship through an untrusted BMC, which is kind of the cool part there. But in terms, like I haven't seen anything workable yet in having an encrypted or trusted MI channel at this stage. I'd be interested to hear about that if it's ever in progress. But yeah. And the second part of the question.
I was thinking about this. That's another example of I would say, a new use model, asynchronous.
Asynchronous, yes. So we're essentially asynchronous anyway, because we're using a standard sockets API. Unlike the in-band interface, which is all IOCDL, we have a asynchronous transmit receive. So MI itself is, well, the interface we provide for MI is asynchronous because you're doing a send message, receive message. But the API that we're exposing through libNVMe matches the existing API for that. So it's a synchronous function call at that point. But there's nothing stopping us from doing a callback mechanism or something kind of more IOU ringy perhaps, because it's just a plain socket. So we can use anything that supports kind of socket asynchronous methods over that. Okay, cool. I think we're out of time. Thank you very much. Do let me know if you'd like to chat about NVMe things or Swordfish things or MCTP things. Like I said, we've got some resources up, but I will be around this week. Cool. Thanks all.